Welcome back to our series on data handling for statistics. I'm Mark Ledbetter, and this is code along file number 11 and video number 10. So we're going to continue discussing matrices. This is matrices 4. So we're going to clear the environment, and I'm going to Control L to clear my console as well. And remember last time we talked about the transpose of a matrix. I included this code again so that I can have this matrix that I used last time and continue using it. So I copied it over. Okay, so this is our matrix, and you should have the same matrix in your file. Okay. And we also reviewed matrix multiplication. We talked about x times its transpose. In this case, it gives us a 3 by 3, and the transpose of x times x gives us a 5 by 5. So we can always multiply a matrix by its transpose, and we can always multiply the transpose of a matrix by the original matrix. In general, these things are not equal. And remember, the exclamation point means not in this case. Okay, so with our case, I say A prime A, but in our case it was x prime is a 3 by 3, and x prime x is a 5 by 5. Okay, we used x up here, not A. Sorry. All right. Now, we're going to talk about something called a determinant. Now, I'm not going to go through everything I have typed here, but if you're interested, I have put all the information you should need to understand this concept. But the code to calculate it is very easy, but you wouldn't know what you're calculating maybe. Okay, so there's a lot of notation, same notation to denote or different notation to denote the same thing. So what looks like an absolute value sign around a capital letter, where the capital letter stands for a matrix, that's the determinant of a matrix. It's also written det A. Okay, so you'll see that notation in some textbooks, and that happens to be the actual function we use in R, which is nice. Okay. Now, only square matrices, same number of rows and columns, have a determinant. And remember that A primed A and AA primed are always square, so they have determinants. So we'll start with the easiest case, a 2 by 2 matrix. Let's say its elements are A going, we always go across the rows first and then down the column. So A, B, C, D, and it's a 2 by 2, means that the first row has A and B, the second row has C and D. Okay? So the determinant of B here would be, you use the diagonal. So A times D, and then you subtract B times C. Okay, so it's like a cross multiplication, but subtracted with a subtraction in here. So AD minus BC. So let's do an example. Here's a matrix 2, -1, -3, 5, and it's a 2 by 2. Okay, and so here's our B. You can see 2, -1, -3, 5. It's always a good idea just to make sure that you did it right, because we did by row is equal to true here. If we did false, then we would not have gotten this matrix. We would have gotten the transpose of it. Okay, and we only get the transpose of a matrix by accident if the matrix is a square matrix. Okay, so otherwise we would get something completely different if it's not a square matrix. So just a note. So the determinant of B should be 2 times 5, which is 10, minus -1 times -3. -1 times -3 is positive 3. So 2 times 10 minus 3 is 7, and that is what we get. So be very careful with the negative signs. Now, I've written, let's say, matrix A two different ways, A, B, C, D, E, F, G, H, I. And then I've written it with subscripts. The underscore here means it's a subscript. So for the position 1, 1, so the first number represents the row, the second the column. So So this first element here is A sub 1, 1, and then A sub 1, 2, and then A sub 1, 3. So it's the third element of the first row. So again, the second row, the first number is 2. And then the second numbers go 1, 2, 3. And then the same thing for the third row. Now, this is a handy notation when we're calculating determinants because we need these indices or these location numbers in order to do the calculation. Okay, and I'll show you what I mean. So for a 3 by 3 here matrix, you might just learn this formula, but I don't like to just do this formula. I like to explain how it's done, because if you understand how this is done, then you can do a determinant for anything. So what we do is we're going to choose a row or a column, and most people will choose the first row of the matrix. And then what we do is we eliminate, we avoid or eliminate or exclude any elements that are in the same row. So we're going to start with A, element A, and so we'll exclude B and C, and we'll exclude D and G here. And so what we're left with is E, F, and HI. And so we'll take A and we'll multiply it by the determinant of what's left after we cancel out this row, the row it's in, A is in, and the column A is in. Okay? And in this case, it leaves us with a 2 by 2. Well, if it was a 4 by 4, well, then if we, let me do another one. I'll just add to this for now. So let's say it won't be in order, but that's okay. J, oops, K, L, and then we go down and L, so M, N, O, and P. So if it's a 4 by 4 and we start with A, then we would be left with these three, and these three. We'd be left with a 3 by 3, and then we would have to find, we'd take A and we'd multiply it by the determinant of that 3 by 3. And when we're calculating the 3 by 3, we'd start here, and then we'd have a 2 by 2. And as soon as we get to a 2 by 2, we know how to calculate that determinant because we learned that rule up here. So we take the first element times this last element, and then the second times the third. We multiply A times D, we subtract B times C from that. Okay? So you can keep on reducing this until you get to a 2 by 2. It becomes very, very tedious and very time consuming. So it's great that the computer does this for us, but I hope that you see how we can do this, the pattern that we're following here. Okay, so for this 3 by 3, I'm going to take A times the determinant that's left over, that's not the determinant of the elements that are not in the row or column of A. Okay, so it's E, F, H, I. But before I do that, I also, in order to determine whether this is going to be positive A or negative A, I need to take the negative 1 and raise it to the power of the sum of its position. So if it's in the first row, first column, that's a 1 and a 1. So negative 1 raised to I add these together, I get a 2. Whoops, there, a 2. So negative 1 squared is going to be positive. Anything squared is positive. Okay, so that's why I have a positive A here, because I've multiplied it by negative 1 squared. So this is going to be negative 1 squared. Oops, that didn't work very well, did it? Because everything else has to move. Okay. Okay. And so then I have to multiply it by the determinant of this 2 by 2. So I'm going to take E times I minus F times H. Okay. And then I have to do, I go over to the second element of this row because I'm using the first row. And again, I'm going to eliminate all the elements in the row, same row as B, and I'm going to eliminate the elements in the same column as B. So I'm going to be left with D and F, right? So I'm left with D, I'm left with F, I'm left with G, and I'm left with I. So that's exactly what I have here. And I have B times that. But I have a negative over here. Why do I have a negative over here? So I could write this as the positive, and I will do B, and then I will say -1 to the 3rd power. And so I need to line these back up so you can see. Okay? So I take -1 and I raise it to this. Why am I raising it to the 3rd power? Because I'm adding the position. It's in the first row, the second column. So 1 plus 2 is 3. So if I take a negative and raise it to an odd power, it stays a negative. And so you see that the sign is alternating. -1 squared is a positive. So I have a positive A, then I'll have a negative B, and then I'm going to have a positive C. That's just the way it works, because if I 2, and then 3, and then 4. Okay, so 1 plus 3 is 4. So this is going to be -1 to the 4th, and -1 to the even power is going to be positive. Okay, so I will write this. I'm going to move these out. All right, so this is going to be -1 to the 4th power. And then, all right. And so this is C. So what I've done is I've taken C, I've eliminated all or excluded all the elements in the same row as C, and these elements that are in the same column as D, and so I'm left with, C, and so I'm left with D and E and G and H. Okay, so I've got C, and then the determinant of what's left, D, E, G, H. Okay, so now I can not write the negative sign here, and that's what you'll normally see in a textbook or something. You'll just see something like this, and then you'll see the negative here. And then you'll see a positive here. Okay, because they've already incorporated the -1 raised to the power if you're using that first row. Okay, so a lot of textbooks will just do it this way, but what the thing is that I can use any row or any column to calculate the determinant using this same method, and I get the same answer. Okay, so now I want to use, let's see, so what am I, so here I've multiplied this out. I've got, so I've written out what we've done. So here's a -1, and this means raised to the power of, and inside the brackets, oops. So inside the brackets, I got 1 plus 1 because I did 1 plus 1 there. So -1 raised to the power of, and this is how you would write this in R. So if I take this down here, and don't forget the last bracket mark, then it's going to give me, that's not good. It's supposed to be a +1. All right, so this is, what's happening is I've got to put this in parentheses, or else it doesn't, it's saying a negative times that. So if I do this, it gives me a +1. So it's not quite the same. Okay, I left off that parenthesis. We don't need all those parentheses up here. That's going to be confusing. Okay, so we've got -1 raised to the 2 power. That's going to be squared. That's going to be positive. And then I've got -1 raised to the 3rd power. That's going to be negative. So even though I've put a positive here, this is going to be a b times a negative value. It's going to be -b. And then I've got c times, and I've got a -1 raised to a 1 plus 3, which is a 4 power. Okay, and I've calculated the determinant of the 2 by 2. So it's e times I minus f times h. So E times I minus F times H. And for the second one, it's D times I minus F times G. And then it's D times H minus E times G. And that's what I have here. Okay? And so then I've taken and added these two together, and I got the 2 here. And I added the 1 plus 2, and I've got the 3 here. And I've added the 1 plus 3, and I've got the 4 here. And then I left these the same. And then I came down and I said, okay, what is A times negative 1 squared? That's going to be A times positive 1, and it just gives me A times 1. And then I've got B times negative 1 cubed. That's just going to be a negative 1. And then I've got negative 1 to the 4th, and that's going to be a positive 1 there. And so A times 1 is just 1. B times negative 1 is negative B. And C times positive 1 is positive C. And then I still have, oops, I've forgotten my asterisk here. Can't forget that. Okay. And then I have that's multiplied times the determinant, the 2 by 2 determinant that's left here, each of these determinants. Okay, so that gives you in letters, and I know that's messy, but that's the form for it. Okay, so again, I used row 1 in this. I used A, B, and C. I used row 1, but I don't have to. So we could have used any row or any column to calculate the determinant. So here is a general formula. I know it's hard to write in R, so I apologize, but the determinant of A is the sum, and what you sum across depends on whether you use a row or column. If you use a row, you'll sum across I. If you use a column, you'll sum across J. Okay, J will stay the same, and I will change if you go across a column. If you go across a row, or I'm down a column, sorry. If you go across a row, I will stay the same, but J will change. Okay, so what it is the sum of each element I sub j times negative 1 raised to the I plus j power. And then that is multiplied by this determinant that's left over when you exclude the ith row and the jth column. Okay, and this works for any dimension. Okay, any dimension matrix, because you just once if this is a 3 by 3, then you have to determine, in order to calculate the determinant of a 3 by 3, you go through what we just did up here. Okay, choose a column or a row, and you do that. So let's do an example where A is 1, negative 2, 3, 2, 4, negative 1, 6, 1, 8. Okay, so I'm going to use row 1. And so the determinant, so since I'm using row 1, here it is written with symbols. Okay, so I got the negative 1 raised to the 1 plus 1, the negative 1 raised to the 1 plus 2, the negative 1 raised to the 1 plus 3 for the third, for A33, which is this one. So this is A11, this is A12, A13. Okay, and then instead of writing A, B, C, D, whatever, I wrote the actual A subscripts with the I and J values here. So I've got A22, A23, A32, and A33, and that would be a 4, a negative 1, a 1, and an 8 for this first one, because I'm using 1, so I can't use anything in this top row, and I can't use anything in this first column, and what it leaves are these 4 numbers here, that 2 by 2. And so I'm going to go 4 times 8 and minus a negative 1 times 1. So it's 4 times 8 minus a minus. It'll be a plus. Okay? So, but I'm jumping ahead. All right, so here it is written out in notation. And then I'm plugging in the values. So I take the first value. So I'm using row 1. So I take the first element, which is 1. And then I multiply it times negative 1, and this should be squared. So this would be negative 1 squared, which is going to be a positive 1, right? Actually, yeah, I'm sorry, that's just a plus 1. Okay, so that's a plus 1 because it's going to be negative 1 squared. So that's a positive 1. Okay, so I've got 1, that's this element here, and then times the negative 1 squared, that's a positive 1. And then I have 4 times 8 minus negative 1 times 1. So I've got 4 times 8 minus, and then I've got a, I've got it reversed, negative 1, 1. Okay? And then I've got 2, a negative 2, and it's a negative 2, and then negative 1 raised to the third power is a negative 1. So I've got a negative 2 times a negative 1, and then I've got, so that's a negative 2, so that means this row is gone, and then the column here, that's gone too. So I've got 2 and 6, and I've got negative 1 and 8. I need 2 times 8 and minus a negative 1 times 6. So 2 times 8, and I've got these reversed again, negative 1 times 8. Okay, so 2 times 8 minus negative 1 times 6. I'm sorry, did I do that wrong? Okay, so 2 times 8, negative 1 times 6. I'm sorry, I put 8, but it was a 6. Okay, so this is the second one. So that means we don't include the 4 or the 1. So we've got the 2 and the 6, the negative 1 and the negative 8. So we take cross diagonal, so 2 and 8, and then we subtract, and then we've got a negative 1 and 6. And so that's what we've got, negative 1 and 6. Okay, and then the third one, we're left with 2, 4, 6, 1 here. And so, remember that this was a positive 1 because it's negative 1 to the fourth, which is positive. So I've got the 3, which was positive, plus 1, and then I've got what's left is 2 times, 3. So I've got 2 times 1 minus 4 times 6. Yeah, so 2 times 1 minus 4 times 6. Now I simplify. So positive 1, a 1 times a positive 1 is just a 1. A negative 2 times a negative 1 is a positive 2. That's negative times negative here. A 3 times a positive 1 is just a 3. Okay. And so then I can simplify more. So 4 times 8 is 32, right here. And then minus 1 times negative 1 is negative 1, but times a negative is a positive. So I've got a positive 1. You can see where the signs are very tedious, but very important to keep straight. Then I've got 2 times 8 minus a 6 times a negative 1. Well, 6 times negative 1 is negative 6 times a negative is a positive. So I've got a plus 6. And then I've got 3. And then I've got 2 times 1, which is a 2. And then minus a 4 times 6, that's 24. So 32 plus 1 is 33. 16 plus 6 is 22. 2 minus 24 is minus 22. So 1 times 33 here is 33. 2 times 22 is 44. And 3 times negative 22 is negative 66. This comes out to be negative or positive 11. That's my determinant. All that to get that one number. Now, to use column 2, I'm going to see, where is my A? I'm going to go ahead and put my matrix in so I can print it out, okay? So I can see it in the console. Here's my matrix down here. So to do column 2, that means I'm going to start here, and then here, and then here, okay? So I have a negative 2, and that is in the 1, 2 position. So remember, I have to multiply this by a negative 1 raised to the I is 1, j is 2. That's a 1 plus 2 is 3. It's a third, so it's a 1 plus 2. That's an odd power. Negative 1 to the third is going to be a negative 1. So I took negative 2, and then I've got negative 1 raised to the I plus j. I is 1, j is 2. And then what's left is the 2 and then the negative 1 going across, and then the 6 and the 8. So I've got 2 times 8, and then minus 1 times minus negative 1 times 6. So 2 times 8, negative 1 times 6. The second one is 4. That's in the 2, 2 position. So I have 2 plus 2 here. That's going to be 4, right? So negative 1 to the 4th is going to be a positive. And then I've gotten rid of this row and this column. And so I've got 1 and 3, 6 and 8. And so I'm going to have 1 times 8 minus 3 times 6. So 1 times 8 minus 3 times 6. And then the third element of this column is 1. And so that means that I'm left with 1 and 3, 2 and negative 1. So that's going to be 1 and negative 1, 3 and 2. So 1 and negative 1 minus 3 and 2. And then this is position 3, 2. So it's going to be 3 plus 2 in the, I'm going to add as a power of negative 1. It's going to end up being a negative because it's odd. Okay, so I simplify. So negative 1 to the cubed is going to be negative 1. I left everything else the same. And negative 1 to the 4th here is going to be positive 1. And then negative 1 to the 5th is going to be negative 1. Okay, and so then I also multiplied. So I have here, I have 2 times 8 is 16. And then I have a minus negative 1, which is going to be positive, and then 6, so plus 6. And then I have the 4, and this is positive. And then I have 1 times 8 minus 3 times 6. So 8 minus 18. And then I have 1, and this is going to be negative 1. And then I have 1 times negative 1, which is negative 1. And then I have minus a 3 times 2, whoops, which is a 6. So it's minus 6. So negative 1 minus 6. So I've got 16 plus 6 is 22. I've got 8 minus 18, which is negative 10. I've got negative 1, negative 6, which is negative 7. So 2 times 22 is 44. 4 times negative 10 is negative 40. And then negative 1, negative 7 is positive 7. So I've got 44 minus 40, that's 4, plus 7, which is 11. So I've got exactly the same value doing it both ways. Now I can just easily use R to get this. Boom, 11. Much nicer, right? Okay. So there's some properties of determinants, and then we'll call this a video. So we've got the determinant of A is the determinant of A transpose. So let's look at both of these, and I get 11 for both. So that's true. Now, I'm going to let this be C, and notice that the second row is 0. Okay, so that's going to make the determinant 0. Why? Because if I chose this row, okay, then I would have 0 times the determinant of negative 2, 3, 1, 8. 0 times something is 0. And then for the second one, I'd have 0 times the determinant of 1, 3, 6, 8. That's going to be 0. And then I'd have 0 times the determinant of 1, negative 2, 6. So 0 times something is 0. So I'd have 0 plus 0 plus 0. So whether a row or a column is 0, then the determinant is 0. And let's just show that with this. And 0 is what I get. Okay? If any two rows or columns of A are the same, then the determinant's going to be 0. Okay? So this comes from matrix manipulation. It turns out that what I can do is I can add or subtract rows, and it doesn't change the determinant of the matrix. So or the system of solutions. So or the solutions of the system of equations. So because these two rows are the same, I could subtract them and then get 0 for one of the rows and replace one of the rows with the subtraction of these two rows. Okay, so I'd end up with the same matrix as I have up here. So let's see that and prove it. So D is this matrix, and then the determinant, yep, it's 0. If A is non-singular, that means that the inverse exists. If the inverse exists, then the determinant of A times the determinant of its inverse is going to be equal to 1. So here's the determinant of A. Remember, the inverse is solve A. So det A times det of solve A. Let's see what that equals. And it's 1. And likewise, the determinant of A inverse times A is going to be 1. Okay? Also, the determinant of A times B, if that exists, is the determinant of A times the determinant of B. So here's a matrix E. So they have to be able to be so they both have to be square matrices of the same dimension. So E, I'm making it a 3 by 3. So here's this 3 by 3 matrix here. And so I'm going to take the A times E. So here's A times E, a 3 by 3 matrix. If I take the determinant of A times E, it gives me 42,859.73. Remember that the determinant of A was 11, and now we can see that the determinant of E is 38,96,339. If I take this and multiply them, I get this value up here. So this is equal to this. They're the same. Okay. Now, if I take a constant times a matrix and I take the determinant, that's the same thing as this constant raised to the kth power, where k is the number of columns or the number of rows. Remember, it's a square matrix, so that's the same value. So it's c raised to the k power times the determinant of A. So let's see this. So I've got A here. Here's A. Remember A, kind of a simple matrix. So 3 times A is just 3 times every element. So every row I can divide, in this row, I can divide 3 from that. For each element, I can divide that by 3. Each element of this I can divide by 3. Each element of this I can divide by 3. That's 3 times 3 times 3. That's 27. So this is going to be 3 cubed times the determinant of A. Let's prove that. Here is det of 3 times A. It's 297. Remember, det of A is 11. 3 times 3 is 27. Times 11 is 297. So we've just shown that. Okay. Now, the trace of a square matrix is the sum of the diagonal elements. So in R, if you want to write it yourself using the base package, there is no function. So we just do the diagonal of A gives me just the diagonal elements of A. And A was here, 1, 4, 8. And so if I take the sum of that, that's the trace. That's adding up the diagonal elements. It gives me 13, 1 plus 4 plus 8. But the library, the psych library, if you don't have this installed, you'll have to install it first. Remember, to use a library, or to use a package, you have to use the library statement first to load it. So now that I've loaded it, I can use this tr function for trace of A, and sure enough, it gives me 13. Now, this is where we're going to stop for this video. Next time we'll talk about linear dependence of vectors, but that'll be next week. I'm going to consider this video as 2 days worth of videos because it's so long, but this was not a topic that I felt that we could break up into different videos. It wasn't really good for that, okay? So we'll count this as 2 days worth of videos. That way it'll give you a little bit of a break. Please take care of yourself and stay safe because we want to see you here next time.